Good morning, everyone. I welcome you again to today's session. Today, we'll be discussing differentiation and its application. We are going to take the classes in phases. We'll first of all discuss differentiation and then the application will follow. Today, we have some objectives that has been highlighted, and the highlighted objectives are at the end of the lesson, you should be able to define differentiation and derivative. You should be able to differentiate algebraic expressions using basic rules. And you should be able to apply product, quotient, and chain rules to some algebraic expressions. Now, let's take it. Let's start from differentiation. What do we understand by differentiation? Differentiation is the process of finding the derivative of a function, and the derivative of a function at some point characterizes the rate of change of the function at that point. What this is telling us is that the derivative of the functions tells us how fast or slow a change in one quantity affects the other. Let me take that again. The derivative of a function tells us how fast or slow a change in one quantity affects the other. It is uh, it is usually denoted as dy dx. I'm sure some of you must have been familiar with this in your further mathematics. Usually um, it is usually denoted denoted by dy dx. Dy dx. It is sometimes called this dy dx. Sometimes called gradient. Some call it slope. So dy dx is simply telling us the rate of change of a function at some point. So now we can also say that dy dx is designed to find the gradient of a curve at any point without having to draw a tangent to the curve. You know, when you have a curve and you're asked to find the gradient of that curve, before you can find the gradient of that curve, especially on your graph, what do? You draw a tangent, you draw a line, draw a tangent to the curve before you can find your gradient. But in this scenario, you don't need to have a curve for anything to you don't need to draw a tangent to any curve to find your dy dx. So it's a way of finding your dy dx without having to draw a tangent to a curve. It can also be taken as that. So now let's look into the basic rules of differentiation. Basic rules of differentiation. So for some basic rules of differentiation. Now these are the basic rules of differentiation. We are going to discuss just four of them, four basic rules, four important basic rules of differentiation, which are the constant rule, the power rule, the constant multiple rule, and the addition or subtraction rule. For the constant rule, anytime you differentiate a constant, your result will always be equal to 0. And this is an example. The dx of 7 is equal to 0. The dx of 1 million is equal to 0. The dx of 2.5, as much as the value you are differentiating or the expression you are differentiating is a constant, it's going to give you 0. Then the power, this is the power. You know what power is? X raised to the power of n. X as n as its power, while x is its base. Each time you want to differentiate any expression of this form, what do? You first of all bring the power. You know you are differentiating xn here. You want to differentiate xn. You first of all bring the power to the front to multiply whatever coefficient s is having. In this case now, for xn, the coefficient of xn here is 1. So you bring n, the power, to multiply the coefficient of xn. So 1 times n will give you n. That's why you have n here. Then you write um, the original expression that you have, and then subtract -1 from the power. Let me give you an instance. Suppose I want to find dd's of 3x, for example, or let me say 3x squared. 3x squared, for example. So if I want to use power, what do? You know, 3x squared has 3 as a coefficient here. So and also has 2, and the x here, the variable x here has 2 as its power. So the first thing I'm going to do is I will bring this to the power of x to multiply the coefficient of 3x squared that I have here, and this will become 2 times 3. That's the first thing. You write the variable again, which what's the variable here? The variable that you have here is x. So and it's taking a power of 2, so you write the whole of that, x squared, and then you subtract 1 from the power minus 1. So this will give us what? 2 times 3 is what? That's 6. X raised to the power of 2 minus 1 is what? 1. You see, at the end of the day, the differentiation of 3x squared will give us what? 6x. You see, this rule, this power rule, can be used to prove that when you take the differentiation of a constant value, it gives you 0. Remember I said this one, DDS of 7 is equal to 0. So let me show you how this 0 was gotten. You know, for 7 now, 7 can be rewritten as, let's say I want to find DDS of 7x raised to the power of 0. Do you know that 7x raised to the power of 0 is the same thing as 7? Is the same thing as 7, because in your law of indices, x raised to the power of 0 is equals to 1. Anything raised to the power of 0 is equals to 1. So this means that I have not changed the originality of my question. It is still 7, but I'm writing it in a different form. So if I want to use the rule of power, what's going to happen here? What is going to happen here is that I'm going to have my 0 to multiply the coefficient of x raised to the power of 0 that I have here, and then I will have x raised to the power of 0 minus 1. Without having to solve x raised to the power of 0 minus 1 further, you can see that 0 times 7 is 0. Anything multiplied by 0 will give you 0. So when you use 0 to multiply all that you have here, what do you have? Yeah, your result is going to be 0. And that is why it has been established that each time you are taking the differentiation of, each time you are taking the derivative of a constant value, what do you do? What do you have? You have a 0 as your result. So that's that. So let me also discuss constant multiple rule. What this is saying is that when you are asked to find the derivative of a function and a constant value, what do? You can always factorize the constant value out before you take the derivative of whatever function of x that you have. Let me give you an instance. Suppose I am asked to find the ddx of, let's say ddx of 5x, ddx of 5x now. In this scenario, we can see that 5 being the coefficient of x is a constant, right? So this can be rewritten as 5, I'll bring the constant out, 5 dds of x. So I'll be left with the variable. Since you know I can split 5x as 5 times x. So in as much as the expression that you are being given is associated with product and it can be separated like I did here now, you can factorize the coefficient outside the derivative. Can factorize the coefficient outside the derivative. You bring the coefficient out, and then you take the derivative of the variable that you have. So now that I have dds of 5s, it can be written as 5 dds of ds, which means that I have factorized the constant out. That means I don't have too much business with the constant, and then I'm going to differentiate what? The variable that is here. Remember, this variable is variable x and is having a power of 1. Anything raised to the power of 1 will give us the original number, right? So now I can now apply the power rule to this one. If I'm applying the power rule, don't forget that you have 5 outside, and then you open your bracket. What would this give us? This will give us, the coefficient of x raised to the power of 1 here is 1. It is not just written because it is 1. So that means, and there's another one coming here. What's going to happen? I'm going to have 1 times 1, right? 1 times 1, x raised to the power of what? X raised to the power of 1 minus 1. No, I'm not sure if you can see that. Because x raised to the power of 1 minus 1. So what would that give us? So you're having 5 times 1. 5 times 1. 1 times 1 is 1. So 5 times 1 will also give us what? 1. So eventually I'm going to have, 5 times 1 will also give us 5. Eventually we are going to have x raised to the power of what? 1 minus 1 is 0. Remember we said that any trace power of 0 is equals to what? Is equals to 1. So this is going to give us 5 times 1, and this is 5. I hope you can see that. So each time we have something similar like this, you should be able to differentiate them. You can factorize uh, the coefficient out, and then take the derivative of the function of the variable that you have, or the expression that you have. Take the derivative of the function of x that you have. So now the next one is addition and subtraction rule. For addition and subtraction rule, when you have two different expressions that is associated with a positive operator or a negative operator, you can take the derivative separately. You can take the derivative of f of x separately, and you can also take the derivative of what? G of x separately. Now, let me give you an instance of what I'm saying. You know, this is a function of x. G of x is also a function of x. So let's say for f of x now, I want to find the derivative of, let me manage this space before. Okay. In fact, let me open a new page. I want to take the derivative ddx of 2x plus let me say 2x squared plus 3x for an example. Remember I said, remember the we are trying to prove the basic rule. We are trying to apply the rule of addition, and we are trying to apply the rule of addition and subtraction. So addition and subtraction. So look at it now, f of x and g of x. So in the example that I'm trying to solve, you will see that 2x squared is my f of x here. This is my f of x, and 3 of x is my what? G of x. So what this is invariably saying that, you know, operation addition as is an operation binding f of x and g of x. So what the rule is saying that it can as well split the function, the derivative of the function, irrespective of the operation, whether it's positive or negative. Now, so this is saying that you can rewrite this one as ddx of, you take the f of x first, 2x squared, then you put your operation plus, and then you take ddx of what? 3x. If we follow the power rule is popularly known as the general rule for solving differentiation. It's a general rule for solving differentiation. So if I want to find derivative of 2x squared, now this one will become 2 times 2 x raised power of 2 minus 1, right? And this one will become, remember that this has 1 at its power, so this one will become 3 times 1 x raised power of 1 minus 1. At the end of the day, what do you have? You have 4 x raised power of 1 plus 3 x raised power of 0, and that's going to give us 4x plus 3. So this is giving us 3 because x raised power of 0 is what? 1. 3 times 1 is 1, and that's all.